back is best. Okay, I see some people waiting in anticipation. See some people rolling with their eyes, and they are in the right to do so. There is no best growing back. Let's face it. Each, like your situation, needs a different growing back than another person's situation. For example, let's say your process requires the bag to be autoclavable. You need different material. For example, you work in a dirty room. You need a very secure bag. You have a very rough production process. Then you need very strong bags. But there's one thing that's a bit less tangible, and that's the gas exchange. If it wasn't for the gas exchange, we would just sell plastic bags and seal them. No contamination at all. But yeah, you get the issue. Mycelium will suffocate and die. That's why we need good filters. So this is a happy mycelium. It can breathe, can draw in the oxygen from outside, and get rid of the excess carbon dioxide. So, as a company, SACO2, how do we react and anticipate to this? Is there a way to benchmark certain filters? Maybe we can try to put a number on a filter material. Like this filter material is a 2.5, this one is a 5, so it gives double the gas exchange. Is it possible? Let's find out. We are in the industry, so first we have to try to find easy answers. Let's just look at the tech sheet, the spec sheets of the material. This is Tyvek, very common. So if we find something, it will be over there. So we see some things related to strength, but at the bottom there are two interesting parameters related to air permeability. Looks nice, but there's a catch. This is not really the same as we have during the incubation of spawn and substrate, because what we have is just the gas exchange at relatively atmospheric pressure, and these measures are really a measure for air permeability at an overpressure. So it's something completely different. So there's a need, not really for an ISO standard, but for a good standard in our industry. So we don't find any here. Let's go back to the drawing board. Yeah, a couple of years of twiggling around, and then we have this, the machine that Jan showed. For the ones that weren't present before, so it measures oxygen and carbon dioxide, but it can do a lot at the same time. You can measure like 20 bags in parallel, so that's really time saving, and it's good for repeatability. This is what Jan talked about. I will talk about something different. How can we use the same machine to benchmark filtered materials? So this is a setup. It's the same, but we get rid of the bags, and we hook up standard sized boxes, standard volume, and we incorporate standard sized filter material. So what do? We flush the boxes with carbon dioxide, so you have very high carbon dioxide inside the container. And yes, it can happen. You saw in the previous talk that the carbon dioxide levels inside the bag can really go up. So at the start of the experiment, we have high carbon dioxide, so a very large gradient over the filter. If the experiment continues, the gradient declines. It means that if it declines, it means that it's almost equal to the ambient environment. Similar story for oxygen, but at the opposite. To not make things complicated, I will focus on carbon dioxide. So if we translate what I just said to a graph, you have this. Over time, you have a gradient over a filter that will decline. So at the start, you see that we have a 10% gradient, and towards the end, due to passive diffusion to the environment, you have almost zero gradient over the filter. If we transform this graph, this is way more interesting, we can see the gradients on the x-axis, and really the flow, how much carbon dioxide goes through the filter, is on the y-axis. Makes intuitive sense, high gradients, high flow. So low gradient, low flow. But what is really interesting is this linear relationship you see here. If we look at the slope of this curve, what does it represent? The diffusion coefficient. And if we standardize it with a filter area, we have a relative diffusion coefficient. Remember when I said it would be nice to have one value for a filter material? Yeah, here it is. It's the relative diffusion coefficient. So when we compare different filter materials, we would typically look at this value. So if I refer to diffusion coefficient, it will be this one. Let's wrap up with 3 small cases. First, let's benchmark our own portfolio. Secondly, let's source some new filter materials. And to finish, yeah, it's the pinnacle, custom bag design. Make new bags, make them better. So when it comes to benchmarking our own portfolio, we did it with the polyethylene microsacks. So what are they? They are typically used to incubate substrates in a bulk sterilization system. They have a double filter system. So you have a membrane filter on top, and underneath you have a film that is perforated. If you look at the membranes first, we have 3 standard membrane types. Our G-type filter has the largest gas exchange, and our Tyvek filter has the least gas exchange. And it's very nice that we have these results because it corresponds with what we thought intuitively. Now let's incorporate this inside of the bag. We have the perforated film, and as you might think, this perforated film has also very high impact on the gas exchange. Here I compare a 3-row perforation pattern with a 6-row perforation pattern, and as you can see, the 6-row perforation pattern has almost double the gas exchange compared to the 3-row perforation pattern. So this really enhances the understanding of our own products and enables us to fine-tune a bag for the correct gas exchange. Now let's source some new materials. Oh yeah, this picture, you already saw it, probably wondering what the heck is it. It's actually some subset of materials we sourced and benchmarked over the years. There were even too much to fit into the picture, but I did my best. Here a small subset, so we wanted to find replacements for our standard filters. And as you can see, this 55B, for example, is very similar to our G filter. So it shows potential to replace this filter type. On the other hand, we see this 85A really doesn't, it's a bit disappointing, so we can immediately discard it and save a lot of time. Now this custom bag design. So I will wrap this whole story up with a customer story. So we had a customer, they had their own bags. They were very happy about the gas exchange, but all the other things of the bags were really not nice. So they came to us and they asked, oh, design me a bag, but we want the same gas exchange. Okay, so what did we do? We benchmarked their filters, and with a small formula you can see here, we could calculate quickly what the optimal filter area would be inside the bag with our filter material. This really reduces the amount of trial and error you need to do with the client to come to the right bag. Secondly, before we ship it, the new bags to the client, we can do a benchmark of the whole bag, and this reduces the time even more. So I think we can wrap it up here. We already had a lot to talk about, but just keep in mind there comes a lot of experience by designing these bags, and this new thing we have, this quantification, really enables us to enhance this experience and have some solid facts. What I didn't talk about also is the position of the filters, which can be very important. It might be better to have multiple small filters compared to one big filter. But as Jan said, we are really happy to talk about this kind of stuff. So come and visit us. We would like to thank Johan and the organization for being able to be here. And I wish you a very nice Congress. Thank you.
Thank you, Frederik. You were very nicely in time. I was wondering, where do you set the boundaries? What is good enough and what is too much? I can imagine that if you exchange oxygen and carbon dioxide, that you also exchange water vapor. So the more exchange, I'm assuming you're losing more water in your bag, and that can create another stress. So where do you find the boundaries?
Okay, so there's a small distinctions between water vapor transmission rate and gas exchange. They somehow correlate, but so for certain applications we want the water out, and for others we want it in. So, but it's not a measurement. For gas exchange, we typically see that it's very difficult to give. It's almost never enough. So, yeah. Can you maybe, I'm losing a little bit track, so.
Well, it was just a thought that came to my mind. So you basically already said it's the highest gas exchange possible is probably the best, if I understood you correctly.
But actually the thing is, we have this fantastic products at work. We already have it for 10 to 20 years. But now is the first time that we really can put like value on it. And by doing this, we can really set the boundaries. Like, this is the maximum, this should be the minimum. And water vapor transmission rate is an additional measurement you should do in addition to the carbon dioxide and oxygen levels.
Okay. There's a question by Jan.
It works. Okay. So there's not really a perfect gas exchange rate or water vapor transmission rate. I think it depends on the specific situation. So like Frederik said, we have been working with imperfect fungi where we want to dehydrate substrate as quickly as possible so we can harvest the spores. And well, if you are going to produce substrate for mushroom fructification, you want to keep the water in as long as possible. So it depends on what you are trying to do, and we can tackle this problem independently for everybody who has an interest in having a bag made for them.
Okay, there's more to it that came to my mind. Jenny.
Hi, have you measured the respiration rate of the material at different points during development? Because, and any idea how variable it is? Because presumably the gas transmission rate has to equal the respiration rate of the product inside. So.
Very good question. So if we look at respiration rates, it is more closely to Jan's content. But if you talk about respiration rate and these phases, you can see that in the different phases you have another gradient over the filter. So in the larger stages, you have a larger gradient and the gas will exchange will flow quicker out, and it can just be calculated with this formula. So I don't know if that answers your question or not.
I would have thought, I would think, as a post harvest physiologist, I would measure the respiration rate first and then calculate the gas transmission rate that you need in order to achieve an equilibrium.
Yes.
But hasn't been
So-
done? Because it could be quite variable, and that will affect the type of filter that you're going to use.
I know where you're getting at. So we have these bags, and they are a way to, like, to produce mycelium. And there are some pieces of the puzzle you need to figure out. So for one, we have this in vivo test where you really measure concentrations in the bag. For the second, we have these ex vivo tests where we can have like coefficients that can model the air going out. So if we combine the two, we can have a complete model of the growth inside realistic conditions, because that's where we grow them. We grow them inside bags. So this is the most realistic situation possible.
Okay, there was another gentleman from the back, gentleman with the cap.
Do you think with this research that you're doing that bag producers in the future will have a number, a gas exchange number for their bags in the future?
It would make sense that we set a standard. And for example, if you have a bag, you could give a specification. This is the total diffusion rate of your bag. And then you can compare it with other bags. So it would make sense to have a standard that really resonates well with what we need as an industry.
Okay, last question, please.
Have you seen any chance that temperature or atmospheric pressure may affect relative diffusion rate?
Okay, let me think this through. So, actually, we don't have that stable of a temperature, and it doesn't affect the results. So this indicates that the influence of temperature, etc., is really too small to be significant, to have significant impact on the diffusion rate in practical environments.
Okay, thank you. Thank you, Frederik. So,
Yeah, it was a pleasure. Thank you.
yeah, well.